Remember back in Unit 5 when we learned about Hess's law, that whether it was an enthalpy change, delta H, whether it was delta G or delta S, that if you know the enthalpy change for one reaction, you can flip that reaction, you can double that reaction, you can add the enthalpy change of one reaction, or Gibbs free energy or entropy. You can add those, you can add the delta H of one reaction and the delta H of another reaction to get the enthalpy change for a third reaction. And again, you can do that with delta G's as well, and you can do that with entropy as well. That if you know the enthalpy, the Gibbs free energy, or the entropy for a reaction, you can add those together to get another the entropy or enthalpy or Gibbs free energy of a different reaction. Okay, you can do something similar with equilibrium constants as well. Okay, so I just want to review real quickly Hess's law. So Hess's law says that if you flip an equation, then the sign, you switch positive to negative. Okay, if you double the equation, you times the delta H, delta G, delta S by 2. And when you add two equations together, you add their delta H values. Okay, that's what we've already learned. And the reason I wanted to review that is because you do something very similar with equilibrium constants, but you don't do the same thing on any of them. When you flip them, you don't take the negative or positive of it. When you double it, you don't times it by 2. And when you add them together, you don't just add the KEQ values. Okay, so just remember that with Hess's law, that is what you do. But with equilibrium constants, we're going to do all of these things. We're going to flip them, we're going to double them, we're going to add them together. But again, you don't do the same thing that you do with Hess's law. So if you think about it, here's a forward reaction. N2O4 is in equilibrium with two NO2s. And obviously, the equilibrium constant expression is going to be the concentration of NO2 squared over the concentration of N2O4. So if we flip that equation and we make these, the two NO2s, the reactants, and this the product, what do you do with the equilibrium constant? Well, of course, you write it the same way, but now this is the product. So N2O4 is going to go on the top, and the NO2 squared is going to go on the bottom. So what does that do to our equilibrium constant? If you flip a chemical equation, what does that do to your equilibrium value? Well, 1 over 6.46 is 0.155. Okay? And notice this little apostrophe afterwards. Don't worry about that. That's not something to worry about. That just means a different, it's basically the same equilibrium constant, but just we've changed it a little bit. So again, that apostrophe just means that it's a different, basically it's a different reaction, but based on this reaction. Okay? So what do you do when you flip a chemical equation? It is the reciprocal. Okay, you take the reciprocal of the one written in the reverse direction. And again, that makes sense because you have to take what happens to your equilibrium constant expression. It's flipped. Okay, you've taken the products and they're now the reactants, so you flip those from the bottom to the top, etc. Okay. Now, so that's if you flip an equation. Remember, you can never have a negative equilibrium constant. It couldn't be, for example, here, you couldn't have negative 6.46. That never happens. The lowest equilibrium constant you can have is very, very close to 0. It can never be 0. It can never be less than 0. Okay, so this idea here of when you flip it, you take the positive or negative of it, that doesn't happen. Okay, number 2, what else can you do is what happens if you double everything. Okay, so if you multiply everything by 2, so instead of just N2O4, now you have 2 N2O4s and 4 NO2s. Again, think about what that does to your equilibrium constant expression. For your new equilibrium constant, now you're going to have NO2 to the 4th power and the concentration of N2O4 to the 2nd power. Okay, now overall, what does that do to your equation? If you multiply everything by 2, you've basically squared everything. Okay, so when you multiply everything by 2, so the equilibrium constant of a reaction that's been multiplied by a number is the equilibrium constant raised to a power equal to that number. Okay, so if we multiply everything by 2, then you take that same equilibrium constant. So you would take that 6.46 and you would square it. Okay, and that would give you a new equilibrium constant. Okay, and again, why is that? Well, because those values are now double what they used to be, but they're raised to the power. And then our last one, what happens when you take two equations and add them together? It is the product, which is the multiplication of the equilibrium constant. So see how this is really similar to Hess's law, but it's a little bit different. Every single step is a little bit different. So when we add these two equations together, we don't add the equilibrium constants, we multiply the equilibrium constants. So the overall equation is just like in the past. Things that are the same we're going to cancel. So BR2s are going to cancel. So the overall equation is going to be 2NOBRs plus Cl2 is in equilibrium with 2NO plus 2BrCls. Okay, and the equilibrium constant for that reaction, we're just going to take 7.2 and multiply by 0.42. And we get 3.0 would be the equilibrium constant for that one. So when you flip an equation, you take the reciprocal of it. Okay, when you multiply an equation by 2 or 3 or 4 or 1/2, then you raise it, then you take the equilibrium constant raised to that power, to the second power, the third power, maybe to the 1/2 power. Okay, and when you add two equations together, you multiply their equilibrium constants together. Okay, here's a couple of examples. Again, we haven't talked about SP yet. Don't worry about that. Okay, determine the value of K3 for the overall reaction. So it looks like, again, things we can cancel that are the same on both sides. That silver, that chlorine, and one of these chlorines cancels. So we've got AgCl and Cl minus, and then the AgCl2 minus. Okay, and clearly we're adding those two equations together. We don't have to flip anything or double anything. So we're just going to take those two equations. So K3 in this case is just going to be 1 times 10 to the negative 10th times 1.8 times 10 to the 5th, which is equal to 1.8, that same thing, 1.8 times 10 to the negative 5th. No, sorry, is that negative? Yeah, to the negative 5th, sorry. Yes, absolutely to the negative 5th. That's to the negative 10th. Okay? Here's another one. Two equations. Determine the value of the equilibrium constant Kc for the following reaction. So here we're going to have to do more than just add them together, because right away I see two HFs. Here I just see one HF. So I am going to double that first equation. So that's going to become 2 HFs in equilibrium with 2 H pluses and 2 F minuses. And Kc for that is now going to become 6.8 times 10 to the minus 4th squared. And then I need C2O42 minus, and I need it as a reactant. So it's a product, so I'm going to flip that second equation. So that's going to become 2H pluses plus C2O42 minus in equilibrium with H2C2O4. And what do I do with that equilibrium constant? I'm going to take 1 over 3.8 times 10 to the negative 6th. Okay, and now the 2H pluses are going to cancel. And so we're going to end up with 2HFs, the C2O42 minus, the 2F minuses, and the H2C2O4. Okay, and now we're going to, so to combine those two equations, what do? We multiply them. So I'm going to take 6.8, and I don't really care what the answers are in the middle. 6.8 times 10 to the minus 4th squared. And again, answer, don't care, times, and then I'm going to put in parentheses, 1 divided by 3.8 times 10 to the minus 6th. And I get an answer of, don't need it in scientific notation, check and see if your answer is the same. I get a Kc for that equation of, I'm looking at significant figures, those both have 2, so Kc would equal 0.12. For that one. Okay, example number 3. We've seen this table a few times. So let's kind of just skip ahead here. Using the data table, determine the value of the equilibrium constant for the reaction represented by the equation below. Okay, so first of all, they give us lots of information. We have to use the equilibrium values, okay? So initially, remember, we had some reactants, but we had no product. And really, not until we got to times 7 did we actually reach equilibrium where they didn't change anymore. So it doesn't matter which of these three that you use, times 7, 8, or 9, because they're all the same. So first of all, our equilibrium constant expression, these are gases, and then these are all atmospheres. So unless they're a little bit more clear, oh, they do say Kp. Okay, good. Okay, so Kp is going to equal the pressure of Cl2O, and that has to be squared, over the pressure of Cl2, again squared, times the pressure of O2. Okay, so now let's put those numbers in there. The pressure of Cl2O at equilibrium, so here's Cl2O at equilibrium was 0.25. And again, don't worry about units at this point at all. No, not even at this point. So 0.25 squared over the pressure of Cl2. So again, here's Cl2, also 0.25. And that, again, real easy to forget those squared there. So 0.25 squared, and then times the pressure of O2 on the bottom there. So that's 0.38, and that is not squared or anything. Okay, and we can kind of see here, 0.25 squared over 0.25 squared, those are going to cancel. So we're really left with just 1 over 0.38, which again, they wouldn't expect you to be able to do. You could approximate it. So 1 over 0.38 equals 2.6 is the equilibrium constant for that reaction. Okay, and then part B says using the value determined in part A. So remember, even if you don't know the answer to part A, you would make up a number, use that correctly in part B. Determine the value of Kp prime. That's what that apostrophe means, or prime means, for a different reaction based on that previous one for the equation shown below. So what have they done differently? It looks like the equation is the same, other than they have doubled everything. They haven't flipped anything. They're not adding anything together. So they've taken this equation and doubled it. So all you would have to do is you would take your answer, 2.6, and you would square that answer. So 2.6, and again, I'm using my real answer. I rounded this to 2.6, but again, if I'm going to do some more math with it, the best way to do it is to use your actual answer. I don't know if it changes anything or not, but I get a final answer of 6.9 as the Kp prime there. Okay? And that's basically, there's no fancy name for it like Hess's law, but you just have to, again, the real understanding here is making sure you don't do Hess's law. Make sure that when you flip an equation, you take the reciprocal of it, don't take the negative of it. When you double an equation, don't double it, you square it. And when you add them together, add two equations together, you must multiply them rather than add the two equilibrium constants together.